Hello and welcome to another video of Learn with Vishram Dasala. Today we'll be learning about refrigeration and liquefaction system, ideal and reversible. So it is important to differentiate between refrigeration and liquefaction system. A refrigeration system or cycle is essentially a closed system operating at a steady rate and where only work and heat are exchanged. In essence, a refrigeration system absorbs heat at a lower temperature level and rejects it at a higher temperature level. This system involves a compressor, a heat exchanger, a throttle expansion valve, and a liquid reservoir evaporator. The system is normally employed to supply a predetermined quantity of refrigeration and at a fixed temperature. The means of performance of a refrigeration system is called coefficient of performance, COP. The latter term is defined as the energy removed from the source divided performance, COP, divided by the work required to remove the energy in question. If the energy heat is to be removed is Q by the Q and work W is required, then the coefficient of performance or COP is given by the formula COP equal to T1 divided by T2 minus T1, where T1 is the lower temperature and in such instance COP is greater than the unity. Vapor compression system. In vapor compression system, using refrigerants such as ammonia, pheromones, which are easily condensed when compressed and are expanded in dual phase, as in pressure enthalpy molar chart, which is more convenient to use than the TS diagram. The energy balance is as follows: heat absorbed Q equal to Hc minus Hv, it release as Q equal to Hd minus Ha, work required W equal to Q1 minus Q2, so equal to Sc minus Sv minus Sd plus Ha equal to Sc minus Sd. So since Hv and Ha are same, equal, COP equal to Sc minus Sv divided by Hd minus Ha. Where H is the enthalpy. As a rule, the COP of vapor compressor system is greater than 1. As noted, the simplified expression COP equal to T1 divided by T2 minus T1 cannot be used for refrigerants using cold gases such as nitrogen. Enthalpy A, B, C, D. So these are the value. Liquid region, superheated region, compressor, two-phase region. So vapor region, liquid region. So this is the way of expansion, this thing. Whereas refrigeration works under that rule only. Absorbs heat at lower temperature. It absorbs heat at lower temperature and rejects, and at lower temperature it goes and it absorbs heat from the system and it releases to the atmosphere heat. Wow, wow. Liquefaction system. Now how liquefaction system works. High pressure free expansion in enthalpic Linde-Hampson system. In a liquefaction system, figure 1.3 and 2.3, the refrigeration duty Q is the theta now. Let's say the 1.3 this. Alright guys, have a look. And 2.3 2.3. Sorry. The liquefaction system in figure 1.3 and 2.3, the refrigeration duty Q is replaced by a continuous withdrawal of the finite liquid M from the reservoir. The uncondensed performance of the gas is returned to the system in concurrent heat exchange, and the liquid is removed from the system as product or from further treatment. In the liquefaction system, identical to a Linde-Hampson free expansion cycle, the overall energy balance around the simple system of heat exchanger, throttle valve and reservoir is as follows. MH2 will be equal to M minus MF H1 plus MF HF. Here A equal to A plus C, so B equal to enthalpy entering a heat exchanger, C equal to enthalpy leaving at heat exchanger, and D is enthalpy leaving with a liquid product. And if the portion liquid is proportion liquefied is MF by M, then the liquid Ly is Y equal to H1 minus H2 divided by H1 minus HF. Since the term H1 and HF are constant, it is obvious that the yield increases as the temperature H2 at the inlet of the primary heat exchanger decreases. That is to say that by pre-cooling the system, the overall efficiency of the cycle and the liquid production increases. Incidentally, the same principle is applicable to a refrigeration system. Linde was well aware of this application and used as ammonia pre-cooling refrigeration cycle in a later development of the high pressure system to improve a production liquid. Cloud intertropic system. The cloud system replaced the throttle expansion valve with an expansion machine, either reciprocating or centrifugal, which creates work, thus eliminating the increase in entropy. At least theoretically, the throttle valve is not completely replaced in order to avoid the formation of liquid within the expansion unit. From figure 2.6, it can be seen that the gas is compressed isothermally at ambient temperature. Then it passes through a heat exchanger to be cooled to be predetermined temperature countercurrent to the uncondensed gas returning from the evaporator condenser. A portion of the pre-cooled gas is sent to the expansion machine where it reaches its dew point. Then it is returned to the liquefier exchanger to condense the remaining portion of the process here. The remaining portion of the air is cooled by returning air from the expander. It is then sent to the throttle valve for free expansion and condensation. In the evaporator condenser, sometimes called the liquefier, the expansion machine is loaded with a oil brake for very small plants, with a motor generator set for large plants or booster compressor for very large plants. The overall energy balance around the heat exchanger, expansion machine and the liquefier applying the first law is as follows. MH2 equal to M minus MF H1 plus ME HE minus H3 plus HF MF HF. A enthalpy entering the first exchanger enthalpy leaving the first exchanger and re-entering the compressor, enthalpy differential across the expander, enthalpy of liquid withdrawal from the system. The yield is y equal to h1 minus h2 divided by h1 minus hf plus r h3 minus hg divided by h1 minus hf, where r is the rate of flow of refrigerant used in the expander. Okay, yeah, slowly we'll get it. Okay, thank you for watching. See you another video. Take care. Bye bye.